All right, I will be presenting Bayesian line detection for redshift fitting for James Webb Space Telescope galaxies. This is joint work with Bonneville, who's since graduated, as well as Sarah, Galen, and Claudia. Okay, the biggest shift since the last time I presented is that we have sort of moved from focusing on Euclid to focusing on James Webb data. This wasn't a huge change for kind of our approach because we were trying to build a general model for this, but James Webb had nice data available. So, okay, so our scientific goals here are going to be fairly generic, but we're looking for emission lines, and we're curious if they're present in any spectrum that we observe. So, as I said, this could be from different telescopes where we're focusing on slitless spectroscopy. And then if emission lines are present, we would like to figure out the redshift for a galaxy. So in kind of statistical jargon, we're doing a model comparison. So we're looking for either the model being there's no lines present or at least one line is present. And then given that there are lines present, we would like to provide an accurate estimate of redshift with some kind of a quantification of uncertainty. Okay, so this was the toy kind of simulation that I showed in the fall. So what we were thinking back then was this is motivated by Euclid, and we have a constant background, and then we have some emission lines here that are fitted as basically Gaussian line profiles. But here we have some real James Webb data. The switch to lines with rectangles is just denoting that this has been like pixels for the data. It could have the same representation with points. These dashed blue lines are the reported errors along with the flux values. But what we see is, we have something that looks like a line that we hope to pick up. We have maybe a constant background, and then we also have a kind of detector gap to adjust for. Here's another example. We're getting farther from that kind of assumed constant background. We have a big line. Again, we have a detector gap. And then here we have something where it's hard to see a line and the background is, certainly not constant. So what we've been doing in the meantime is sort of extending our model to account and fit to this real data. Okay, so the kind of key bits for our model are we have these known lab frame wavelengths that correspond to the emission lines that we're looking for. And their relative locations are all driven by redshift. This is kind of the key piece to our parameterization that I'll show in a second. And we're thinking of the mean, so the bit that doesn't depend on noise, as being some background process with some mixture of these signals on top. And then we also need to account for observational error, and then there's some dependence amongst pixels induced by galaxy size and things like that. Some extensions that we've done since the fall are basically moving to a more flexible model for the background to handle these different shapes. We've added a few additional parameters, for instance, adding a scale factor to help adjust for kind of systematic under reporting of measurement errors. We've been dealing with the kind of actual model structure and choice of priors for signal intensities, things like that. And then a big change is the way that we're doing computing now. It's an approximate approach. It's no longer based on MCMC. It's much faster. That is like on the order of seconds to minutes instead of hours to days. That was a big improvement. Cool. Okay, so for the actual guts of the model, we have emission lines. And so these are the lab frame wavelengths for the 12 or 10, no, 9 elements that we're considering. And so these values we're taking as known, and this corresponds to redshift of 0. And something that'll be important later is that these elements highlighted in blue are deterministically related to their neighbors in terms of their signal intensities. So this is kind of a snag that we had to deal with as we're building out the model. But in essence, we have 12 lab frame wavelengths to start with. And we can relate this to what we'll actually observe through this redshift relationship. So these xk labs, those are just the numbers from before. And then they're shifted into the observable range by this relationship, where redshift zeta there is an unknown quantity that we're hoping to estimate. Okay, so as we're building a model here, for the actual observed flux densities, take the ith pixel, y sub I is the flux. We have an intercept term. We have now a flexible background function. And then we have this mixture of signals. So we have, for our 12 lines, we have a signal intensity, and then we have a signal function that depends on redshift. And then we have some observation noise. The way that we dealt with the kind of flexible background is it's called a cubic B-spline basis. Essentially, this is a weighted sum of cubic polynomials. So we add squiggly functions up where these betas are parameters in our model that can be learned by the data. The signal function shapes are these Gaussian line profiles that we saw in the original kind of simulation. So the only unknown bit here is this redshift. So for each different line has its own Gaussian, where the mean is corresponding to these redshifted lab frame wavelengths. And then finally, for the covariance structure, we have, ignore this for a moment. These EIs and EJs correspond to the reported standard errors from James Webb. And so if we just thought of like these terms, this would be if we assumed independent pixels and didn't have this kind of scaling factor. So here, sigma squared, when this is 1, this basically corresponds to when we've correctly reported measurement errors. And if sigma squared is bigger than 1, that would be like we underreported or underestimated the error. And so we kind of add this inflation factor to pad things. The second term, the e to the something, is for the dependence. So this is basically a smooth function of wavelength. So these are the pixel wavelengths for each pixel. So when this is small, so when the pixels are close to one another, the dependence is higher, and then it basically smoothly drops off as the pixels get farther away from one another. R here, we're not estimating. This is determined kind of ahead of time based on the known galaxy size for each specific spectrum.
Some question, did you have any pre-existing knowledge about the ADA phase, so the one showing up the amplitudes of the signals?
So you mean in terms of like choice of prior values or
Do you know anything about them, or are they pre-parameters?
They have a prior kind of constraining the values that they should take. And then of course in the no signal model they're set to 0. And then we've sort of like the choice of these 12 lines was made by Claudia, for example, as sort of a reasonable set of lines to incorporate, but nothing really beyond that.
They're not correlated to each other other than those that were colored.
Yes, yeah. Okay, so we can do some trickery to basically make this look like a linear model. So here what I've done is gathered up all of the y sub i's into now a vector of flux observations. So this is representing essentially the whole spectrum. We still have our intercept term, just multiplied by a bunch of 1s. The background we had before, we can represent in this matrix notation as x beta. So here, the details don't matter a ton. Essentially, we can represent this in a linear manner. The interesting bit is the signal structure. So for every fixed redshift, this W matrix and this eta vector are kind of well-defined. We know which lines fall into the observable range because the kind of key bit here is redshift is pushing lines in and out of ranges that we could actually observe, and so that needs to be accounted for. So here this notation writing eta as a function of redshift is just to denote that this is only the set of sort of active lines that are in the observable range for this given redshift. Likewise, there are those deterministic constraints I mentioned before. This information is encoded in the sense that we only need to estimate one of the two lines if they're both present in the observed range. So basically, we have constraints that need to be accounted for. When we do that, then we can proceed for every fixed redshift, thinking of this as like a linear model. And then this notation, this capital K, just use it to denote the subset of indices being estimated for this fixed redshift. This will matter in a moment. Okay, so now we have a model. I'll define priors in a moment, but we want to do a model selection, or basically Bayesian hypothesis testing. So again, we have our null model, which is there's no lines, and we have our alternative model, which there's at least one line present. So at least one of these eta k's is positive. The kind of central quantity in doing this is called a Bayes factor. And so what this is the ratio of basically the normalizing constants in Bayes rule when we are, so if you look at just this numerator term, we basically have P, Y of theta, ignore the M for a moment, and then P of theta. This is like a likelihood times a prior, integrating over the parameters. And so this is just the normalizing constant in Bayes rule. Taking the ratio of these quantities is kind of a natural way to quantify evidence for each model. So for instance, when this is 1, we wouldn't have really strong evidence going either way. If this value is much less than 1, this would favor the alternative model, and so on. And in this case, we just have these kind of background parameters, and then the background parameters plus the signal intensities and redshift. Okay, so to kind of complete the picture here, we just need some priors. So for the parameters that are in both the null and signal models, for the intercept and those linear coefficients, we just take essentially normal distributions. Here, those are just the A naughts, B naughts, things like that are just generic hyperparameter values. We have specific numbers, but it doesn't really matter for the sake of presentation. Likewise, we put an inverse gamma prior on the sigma squared. So this is just keeping it positive. Where here we've kind of put our mean at 1. So we assume that our errors are well reported, but we put more weight kind of towards values bigger than 1, suggesting that we probably underestimated our reported errors, or underreported the errors. For redshift, we're considering redshifts within the range of 0 to 4. And we generally consider, here we take scaled beta priors. The simplest of this would just be a uniform over 0 to 4. But really we're thinking of things that are symmetric about 2. So we expect most of our galaxies to have redshift around 2. But we're allowing kind of in this whole range. The signal intensities prior has to be defined conditional on redshift. So we only want to put a prior that's not like point mass on things that are actually in the allowable range for each fixed redshift. And then we can, for instance, have a gamma prior, so something positive. Okay, and so for one of the data examples at least, we can see a kind of a model fit. So this purple line corresponds to this is the maximum a posteriori fit for the model with lines. And then the blue dashed line is the null model without lines. We see both are fairly reasonable looking, although the blue dashed lines are certainly missing the kind of peaks in the data. This is the posterior marginal for redshift that we obtain. And as you can see, it's kind of a nasty posterior. This is why computing is hard in this case.
A single source?
Yes, this is for the same spectrum. Yeah. And there's a couple different estimates we could think of using. So the map, this corresponds to the model fit from before. This would be a redshift of like 1.5. If we took the peak on this marginal that we're looking at, that would be like 1.8. Or if we use the posterior mean, it would be like 2.2. And then the Bayes factor, the log Bayes factor in this case is actually very, very strong evidence for the alternative model. So saying, yes, there is a line present. Cool, ongoing work. We're wrapping this in an R package so that people can use it. And then we're kind of figuring out some details still with the approximation strategy, and we would like a way to sample from the model itself too. Yeah, we're putting this all in an applied statistics paper. So thank you.